if I informally write the formula, it's going to be a sum across all columns. You take the first element in the column. So these are everything from the first row. You alternate signs, starting with positive, negative, positive, and then you take the determinants of this matrix, which I'm calling Aij. You delete row A1J. You delete row 1 in column J. Right. And these are called cofactors, I believe. Okay. All right. Just for completeness sake. All right. Now, okay, so questions about this. So if you have trying to find a maximum minimum function of two variables, you find the critical points, and this is enough to classify maximum or minimum. If you have more than two variables, a bit more involved, you have to find out if this larger matrix is positive definite, and you look at the principal minors. So these upper left blocks, and see if those false determinants are positive. That's the, and this is described in Marsden actually. Okay. Now, back to finding maxes and mins and functions. So to reiterate one of the points I made earlier, we need the gradient of a function dotted with any vector u, where u is a unit vector, which is the directional derivative of f in the direction of u. We need this to be 0 for any direction u, in order for there to be a max or a min. So that's the take-home message from the multivariable Taylor series expansion I was doing earlier. So the only way to make sure of that, you need the gradient to be 0 at that point. That's the only way to get that guarantee. Because in order to make sure that we have a nice horizontal tangent, if it were, for any curve that passes through a point where there's a minimum or a maximum. Okay. Now, a different kind of problem involving finding maxes and mins. Constrained optimization. Okay. The idea is, given a function f with n variables, you want to find a point where f has a max or min, and this is why we generically call it optimization. So however sense you want to look at it, that you're trying to maximize or minimize something. Most people just talk about it as minimizing something, because to maximize f, you minimize minus f. So, so we want to find a max or min, but you have constraints on x. So you want to find a point where there's max or min, but you have given constraint functions that limit the options that you have for x. So you can't just use a regular procedure of finding where the gradient of f is 0 and then checking its matrix of second partial derivatives. That is out. Because you'll find a max or min, but you'll have no way of knowing whether it satisfies these constraints. So we have m constraints that we could have. Most of the time we'll be interested in a case where there's only one constraint. All right. Now, so how are we going to take these constraints into account? We'd like to use, in some way, what we did before, finding a gradient and so forth. But actually we can use those ideas. We just have to do it in such a way that takes all of these constraints into account. So now, this point x0 where we have a max or min is not a critical point of f. So we can't count its gradient being equal to the 0 vector, but here's what we do need. We do need the directional derivative of f at this point to be equal to 0, not for every direction u, but for certain directions u. Which ones? If u is in a tangent space of all of these constraint functions evaluated at x0. Okay. Okay. All right. So, in other words, let's say in a case where we have one constraint. And let's say we're working in 3 variables. So we have just one function, g, we want x, y, z is equal to 0. So if we have 3 variables, we have an equation like this. What does the solution of this equation look like? What kind of geometric object is it? So we have an equation x, y, and z. What kind of object does that describe?
A sphere.
It could be a sphere. In general, what? Yeah, a surface. Yes. I know. So this equation characterizes a surface. So we have a surface, point x0 on the surface, right? Then that point is going to, the surface at that point is going to have a tangent plane, with whatever directions contained within it. So we need the gradient of f to be orthogonal to all directions in this tangent plane. So we do not need the gradient to be equal to 0. We don't need it to have a dot product of every direction, just the ones that lie in this tangent plane. And if we have multiple constraints, it has to be orthogonal to all of them, right? Which most of the time we'll be asking too much. That's why it's a pain to concoct constraint optimization problems. All right. So instead of wanting a gradient equal to 0, this is what we require.